Okay, following on from my previous video, we are now going to look at these three network problems. Now, all three of these are brand new to the course. They're not, we've not looked at these in modelling with algorithms yet, and they all involve bipartite graphs. So we will look at these in more detail as we go through the video. But because they're new, I will explain the problem, and then I will talk about how we get a linear program down for these problems. So the first one is a matchings problem. So here we have a bipartite graph, and we can see a bipartite graph has got two groups, and there are some connections from one group to the other. And our job is, in the matchings problem, is to decide which arcs to select such that as many elements from one group are connected to the other group as possible without duplication. So a practical example of this might be we have perhaps 5 workers, we have 4 jobs that need doing, and the arcs represent which workers can do which jobs, and we want to match a worker to a job. Okay, so that's the problem, and how do we write a linear program to solve this problem? Well, what we're going to do is we're going to use indicator variables again. So just in my previous video, I talked about indicator variables as being variables which are either on or off. So they're either 1 or 0. And they indicate whether an arc is being used or not. So in this case, we're going to assign each of these arcs to a variable, and then that variable is either 1 or 0. 1, we're going to use it in our optimal solution, and 0, we are not using it in our optimal solution. So for example, this arc here will be represented by the variable AW. If AW is 1, that arc is being used and worker A is assigned to job W. If AW is 0, then that means worker A is not assigned to job W. Okay, simple as that. Now we want to maximize the matching. That's what it means to optimize a match. So you want to maximize the number of matchings. I'm just going to call it M, but you can call it P or whatever, or maybe the question will tell you what to call it. And we want to maximize the number of arcs that are going to be used. So that's going to be defined as AW plus AY plus BW plus BX plus CW plus DW plus DY plus DZ plus EY plus EZ. Okay, so we have 10 arcs, and each arc has been assigned an indicator variable. Okay, so that's my objective function, and that'll be true or whatever original bipartite graph you start with. It's just to maximize the sum of all the variables. And we're going to put some constraints in. So we don't want any one of these assigned to more than one of these. Okay, in other words, going back to my practical example, worker A will either do W or Y or none. Okay, it won't be doing both W and Y. So we want either AW or AY or neither to be chosen. We don't want them both chosen. So to represent that as an inequality, we have a constraint. We're going to have an inequality which is AW plus AY is less than or equal to 1. And what that will do is it will force either AW to be 1 or AY to be 1 or both to be 0, which is also possible. Okay. Notice that we have 5 workers and only 4 jobs. So one of the workers, at least one of the workers, won't be assigned a job. Then we repeat that for all of the nodes. So we have BW plus BX must be less than or equal to 1. CW must be less than or equal to 1. DW plus DY plus DZ is less than or equal to 1. And EY plus EZ is also less than or equal to 1. Okay, so that's the 5 nodes on the left. We also have the 4 nodes on the right, and we don't want multiple workers assigned to the same job. So we don't want A and D both assigned to W, so we only need one of these 4 arcs. So we also need the constraint AW plus BW plus CW plus DW is less than or equal to 1. That will ensure that not more than one person is assigned job W. And then we repeat that for the other 3 job nodes, or the other nodes. in the second group. So bx is less than or equal to 1. And then y, we've got ay plus dy plus ey is less than or equal to 1. And then finally dz plus ez must also be less than or equal to 1. Okay. And that is the linear program. If you run that through some software, that will give you the optimal matching or unoptimal matching, which we know will not be more than 4 because there are 4 jobs. And at most, one of those will be chosen, one of those will be chosen, one of those will be chosen, one of those will be chosen. So if we find one that's got 4, then that is definitely the maximum. So that's what the linear program looks like. Now, this problem can also be represented in matrix form. So we might end up with something that looks like this. So we've got our 5 workers and 4 jobs. This is the same graph as we just had. And then we have an adjacency matrix here, which tells us which nodes are connected to which other nodes. And the problem is to maximize the number of ones chosen such that not more than one is chosen in each row in each column. Okay, so that's another way of wording the exact same problem, and that will have exactly the same linear program. Okay, so that was the first of my 3 problems. That was the matchings problem. The second one is an allocation problem. This is usually given in a table, but can be given in a bipartite network. And these will apply to bipartite networks that have the same number of elements in each of the groups. So in this case, I've got 5 elements in one group and 5 elements in the other group. Okay, whereas the matchings problem, you can have a different number in each group. The allocations problem, you will have exactly the same number in each group. Moreover, it will be a complete bipartite graph. So every element in one group is directly connected to every element in the other group. So we have a grand total of n squared connections. Okay, in this case, 25. So we want to allocate A, B, C, D, and E uniquely to VW, X, Y, and Z to minimize the total weight of the 5 selected arcs. So of these 25 arcs, we're going to select exactly 5 of them, such that 1 in each row and 1 in each column is chosen, but we want the total to be minimized. Okay, that's this problem. So how do we go about doing that? Well, again, we're going to introduce our variables, and it's again indicator variables are used for this one. We are either using an arc or we are not. So all of my variables will take the value either 0 or 1. Sometimes they're called binary variables. Okay, and we want to minimize the total cost. So we're going to minimize the total. So if I choose arc AV, then that is going to cost 10. Oops, so I just put a C there as a cost. That's going to cost 10 towards the total cost. Okay, so if that 10 is chosen, that's going to cost 10. If it's not chosen, it's not going to cost anything, but that'll be 10 times 0. Right? And then repeat that for the whole of that row. So we're going to get 10AW plus 8AX plus 13AY plus 11AZ. And if we look at row B, then we'll get plus 10BV plus 17BW plus 10BX plus 11BY plus 6BZ, and so on. And you'll keep going until all 25, in this case, have been labelled as part of your objective. So we're going to end up at the bottom row as being plus 15EV plus 12EW plus 11EX, 17EY, and 7EZ. Okay. So that's the objective. We want to minimize that, and exactly 5 of those variables will be the number 1 in the optimal solution. So we now need to put some constraints in. And the constraints are quite straightforward, because if we think back to this problem, then we just want 1 of these 5 numbers to be chosen. and then one of these 5 numbers to be chosen, and one of these, and one of these, and one of these. And then we also need only one of these, one of these, one of these, one of these, one of these. So that's going to give us 2n, or in this case, 10 constraints. Okay, so the constraint for A, I want exactly one of those to be chosen. So we're going to have AV plus AW plus AX plus AY plus AZ. And we want that to be equal to the number 1. Okay, so exactly one of those 5 numbers will be the number 1, and the other 4 will be 0. Okay, so it's not less than or equal to this time, it is equal to, because we want exactly one of those. And then we do the same thing for the next row. So BV plus BW plus BX plus BY plus BZ is equal to 1. Keep doing all of that all the way down the rows, and then you repeat that for the 5 columns as well. So halfway down we will have AV plus BV plus CV plus DV plus EV must equal 1. Okay, and that will ensure that exactly 1 from this V column will be chosen. Okay, so we'll have all 10 of those. And those are the 10 constraints. We don't need any more. That is all we need. Together with the objective, we'll give them the whole program, and there is the whole program written out. Okay, so there's our objective. We've got our 25 variables with their coefficients. We want to minimize the sum of those, subject to these 10 constraints. What those constraints will do is it will force there to be 5 ones ultimately, and then those 5 ones will give us a total cost. Okay, so that's the allocations problem. And finally, we have the most complicated of them all, which is the transportations problem. So a transportations problem is one where we have, let's say, 3 supply warehouses and 5 shops, and we have a certain amount of stock at each warehouse. So there's a weighting assigned to each node. In this case, I've got 50 stock at node A, 35 stock at node B, and 15 stock at node C. And then I've got 5 shops, and they want the demand. So shop V wants 10 of this 100 stock. Shop W wants 15 of this 100 stock. Shop X wants 20, Y wants 20, and Z wants 35. Okay. So we essentially need to take this 100 units of stock and distribute it amongst these 5 shops such that it equals the demand. What you'll find with these questions is that the total supply will always equal the total demand, just for simplicity. Okay. So the above table represents the cost to transport one stock item from warehouse A, B or C to the customers VW, X, Y and Z. And the table also shows the total stock at each warehouse and the demand of stock for each customer. And our job is to write a linear program which minimizes the total transportation cost such that all customers will receive their demand. Okay, so unlike the previous 2 problems, this one is not going to use indicator variables. And that is simply because, just because this isn't 0, it doesn't mean that all 50 stock goes from A to V. In fact, it's going to be somewhere between 0 and 10. It can't be more than 10 because then V would be overstocked and then there'll be a shortage elsewhere. But the variable AV can either be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10. Okay, so it's not an indicator variable in this case because it's not either just 0 or 1. Okay, I think that's what makes this the most difficult problem. Okay, fortunately, the solution is fairly straightforward. So we want to minimize the total cost. So I'm going to minimize C. And if I take, say, 1 unit of stock from warehouse A and deliver it to V, that's going to cost me 9 monies, or whatever unit that is. But if I take 2, then that's going to cost me 18 monies, because this is the cost per stock item. So it's not just a case of our transfer 10 from A to V and that'll cost 9. No, that actually costs 90 because that is the cost per stock. So let AV be the amount of stock that goes from warehouse A to to shop V, and however many that is, it's going to cost 9 AV to transport that. So that is the first unit of cost, 9 AV. And then I can use the same argument across the other 14 numbers in my table here to give me my total objective. So 9 AV, and it was 13, 12, 10, 9. So that's going to be plus 13 AW, plus 12 AX, plus 10 AY, and then plus 9 AZ. And then I'm also going to have the Bs, 8, 12, 11, 10, 12. So I'm going to get plus 8 BV, plus 12 BW, plus 11 BX, plus 10 BY, plus 12 BZ. And then I'm also going to get my Cs, which are 9, 14, 14, 15, and 11. So 9 CV plus 14 CW plus 14 CX plus 15 CY plus 11 CZ. Okay, so that's my objective that I'm looking to minimize. Okay, now I need to factor in my constraints. So I'm going to put subject to. Now, at warehouse A, I have 50 units of stock, and that needs to be sent out. All of it needs to be sent out because all of the supply equals all of the demand. So across these 5 variables, AV, AW, AX, AY, and AZ, they must sum to the number 50, exactly. So to represent that as a constraint, I'm going to have AV plus AW plus AX plus AY plus AZ. That needs to equal 50, exactly. Okay, so that all 50 stock is distributed amongst these 5 shops. And then to repeat the same thing for B. So BV plus BW plus BX plus BY plus BZ. That needs to equal 35 because that's the supply at warehouse B. And then CV plus CW plus CX plus CY plus CZ needs to equal 15 because that's the supply we have available there. So that meets all the warehouse supply. We also need to meet the demand from the shops. So in this case, let's look at V. I need these 3 numbers, AV plus BV plus CV. I need that to equal 10. No more, no less. It needs to equal exactly 10. So I'm going to end up with AV plus BV plus CV needs to equal 10. And then I'd repeat that for the rest of the shops. I've run out of paper, so I'm going to do that. So I'm going to get AW plus BW plus CW. That needs to equal 15 because for shop W, they want 15 stock. So those 3 need to sum to exactly 15. Then I've got 20, 20, and 35. So we're going to have AX plus BX plus CX equals 20. AY plus BY plus CY is going to equal 20 also. And then finally AZ plus BZ plus CZ is going to equal 35. And if I run that linear program, okay, there's my objective function and there's my 8 constraints, then that will give me the optimal solution. And that will tell me how much stock to move from each warehouse to each shop. Okay. Right, so that's the 3 extra problems that you need to have met on this course. In the next video, we will look at those 3 problems again, but having run those programs through some software, and then we're going to be interpreting the output from those. That will then wrap up the Modelling with Algorithms course. Thank you very much for watching. If you've got any questions, just pop them in the comments below, and I will get back to you when I can.